So welcome to my talk. So first of all, a little disclaimer. So this video is a sort of re-recording of the talk due to the technical setup. This talk yesterday at the Dynamics Days US could not be recorded. So I'm recording this talk the next day, so January the 9th. It's the same slides and I will basically give the very same presentation. So I will explain today a universal route to explosive phenomena. So what's the plan? So the plan is to explain a little bit the results in this first paper that I have listed up here, which is joint work with Chris Bick. And there we are trying to sort of find a universal sort of mathematical description from a nonlinear dynamics perspective of an effect that often is seen in network dynamics, namely that there's a change from something that wasn't a very explosive sort of phenomenon to something that is a very explosive or quick or sudden phenomenon. So as a concrete example, probably fitting reasonably within the times that we are living in, I will give a adaptive SiS model, so a susceptible infected, susceptible epidemic model on a network. And then I will motivate why we are looking at this problem also in more general context in network dynamics and why it's important there. And lastly, I will go through the mathematical details a bit, apply this to the example, and then also I explain this in the context of a coupled oscillator Kuramoto model. So let's get started. So first, a little bit of background for the classical SiS susceptible infected susceptible model. First, in the case when we are not on a network or when we are on a network where sort of everybody is coupled to everybody. So what you do is to derive evolution equations for such a network model is you sort of, first of all, write down the evolution equations for certain macroscopic observables of interest. So here, for example, the normalized number of susceptibles, the normalized number of infected. And then you would also need to write down equations for the normalized numbers of susceptible and infected links, the infected links, and so on and so forth. And you would get an infinite set of differential equations. And if you assume that the sort of second moments, in this case, the susceptible infected links, are approximately given by or even equal to a product of the susceptible population, the number of susceptibles and the number of infected, which is true for all to all, but for general networks will be false. That's why we'll update the model later on. So, but let's assume that that would be true. Then you get these two coupled ordinary differential equations, and these are pretty straightforward to analyze. I think everybody knows this by now. Due to the pandemic, I guess more and more people have sort of looked at this. And what you can do is you can use a conservation law on the population. Again, it's of course a simplifying assumption. Then you sort of get a single equation for just the infected density. This you can analyze. So you divide by the recovery rate gamma, you rescale time, and you define what's called the basic reproduction number, or R naught, which is sort of the infection rate beta over the recovery rate gamma. You get an equation just for the infected population. You linearize around the disease-free state. You get a linearized equation. And then you see that there's a transcritical bifurcation of the soft variety, meaning you have a sort of non-explosive growth of the epidemic at R naught equal to 1. And you can calculate what the endemic state looks like. This is just a formula. It's R naught minus 1 over R naught. And here you at the bottom, you see the bifurcation diagram. It's indeed a soft transition. If you slowly ramp up the R naught, for example, this would mean ramping up the beta, or decreasing the gamma. Then you would get at some point a bifurcation point. And if you go a little bit further, then indeed the stable steady state that you would get is this endemic state, where you have a certain number of the population, this SiS model always being infected. But of course, this is in some sense unrealistic. There were many assumptions in this model that we made that are sort of definitely in practice incorrect. And about 12 years ago, I started to work on these types of models, and one sort of generalization struck me as particularly important, namely putting the model on a network, meaning that actually not everybody is talking to everybody. Well, not everybody can infect everybody. That's a very reasonable assumption, but that there is a sort of network structure to it. And the second assumption that I found quite interesting, which is actually due to a paper of Thilo Gross from 2006 and collaborators, is to put in some adaptivity to make the network adaptive, that people adapt their behavior. And well, here's sort of the adapted version. You are on a network, you have infected and susceptibles. You have a certain standard sort of process again, which is infection. So you have an S and an I. If they're coupled on the network, there's a certain probability beta or a rate beta that you get an infection. There's recovery. If somebody is infected, they recover at a certain rate gamma. And then there's a rewiring, which is the new part of the model, which makes the network fully adaptive, meaning also the topology can change. And this is effectively a social distancing mechanism. 12 years ago, that was all strange, but by now, I guess we are all used to that anyhow. So what you do is, well, if there's a susceptible and an infected, person is, obviously ill, you might not want to interact with that person, try to avoid them, at least for the time being while they're ill. So you rewire your social connection to somebody else because you still want to maybe have social connections. So you rewire to somebody else. If you do that, then you get a from an SI link, you get an SS link. Yeah, and you break the SI link and you get a new susceptible link. And if you put this little extra detail, this rewiring at a certain rate W into the model, the behavior actually changes quite drastically. So there are parameter ranges where the model behaves differently. So how can you find that out? Well, you again write equations for the observables, but now you cannot truncate at the second moment because you cannot just assume that the second moments are given by products of first moments because you need to somehow keep track of the changing link structure. If you do that, then you actually get again, an infinite set of differential equations, and then you truncate at the next order, which means you make a moment closure pair approximation, and you say, okay, triplets are approximated by doublets. So you assume that this product of triplets, for example, the triplet SSI would be approximated by SSSI divided by the density of S. And if you put that in, you get again a closed set of differential equations. It would be 5 equations. You can eliminate 2 by conservation laws, 1 by conservation law of population, and 1 by conservation law of the links, because you only rewired the link, you didn't break it. Again, that's unrealistic, of course, but it's just a principle. You extended the model by the mildest possible extension that might generate a new effect, and then you are trying to study where this effect is coming from. So it's a conceptual model, really. Yeah? To understand the nonlinear effects. If you do that, and if you draw the bifurcation diagram, which you can calculate even by hand, or here this is calculated with MUTCONT actually, so you see that there's still a transcritical, but this transcritical has become explosive. Yeah, so you actually have that the healthy to epidemic transition, if you go over the threshold for certain parameter values, of course, that are put here on the lower left, yeah, you can actually make it so that this transition is explosive. So if you go over this transcritical point by slowly increasing, for example, the infection rate beta, then you actually jump up and you get a very big endemic state. If you would crank down the beta again or increase the gamma, then you would fall down again, and you basically have a region of bistability. And the model would basically mean that now you don't have a non-explosive, but you have an explosive transition. And this explosive transition clearly was induced by the fact that you changed this transcritical bifurcation. And somehow this came due to the addition of this rewiring. So how to understand this? Yeah? First of all, you see that this is a common story, which is one of the main points I want to make. This is not restricted to an adaptive model in epidemics, but you saw this story in network dynamics over the last 15 years developing in all sorts of sub areas. So what's the main elements of this common story that appears everywhere? So the main elements are this. So first of all, you assume that you have a certain network dynamics model. You assume that there's a trivial branch, meaning, for example, everybody healthy, yeah, or everybody having a certain type of property, yeah, everybody playing a certain strategy in game theory, yeah, everybody moving in, for example, one direction or so, yeah. So there's a trivial branch of solutions that maybe for a certain part of the parameter range is stable. And then you assume that if you vary parameters somewhere along this trivial branch, that there's a non-explosive transition that's sometimes called a second order transition, or a second order phase transition, or a supercritical bifurcation, or in engineering a soft transition. You assume that such a transition occurs along this trivial branch and that it's non-explosive. And then people have augmented these network dynamics models, like I have done in this toy example of this adaptive SiS epidemic model. And you get a new model, M star, and you either make the links adaptive or you make it multi-layered, meaning you have multiple coupled network layers that are interacting, or you make a hypergraph or polyadic interaction coupling. And then you see that, well, if you do that for certain new parameter ranges, when you put in the new effect, adaptivity, multi-layer hypergraph coupling, the transition in this M star can become explosive. So it becomes a first order phase transition, a subcritical bifurcation, or a hard transition. So the question now is, okay, does this appear frequently? Well, yes, it does. So I went through the literature and you find hundreds of papers that tell this sort of story. Yeah? So I only restricted myself here to one journal and just to 6 papers to show that somehow you always seem to get the same type of generic story in this nonlinear network models where you augment them. So here are a couple just papers from PIL, Physical Review Letters. And over the last 15 years, and I could have listed more, there are more of these papers in PRL. And in other journals, we find also lots of papers that have the same story, where people see, well, if you change the model, then, well, you can actually make this sort of biostability region, and you can make this transition from non-explosive to explosive by adding this new effect to the network model. So we were wondering, like, how can you actually generically, in nonlinear science, we want a generic explanation for such an effect, and we want a checkable sort of mathematical framework that allows us to apply and say, okay, you know, this is a transitioning effect that we always see if you augment this, this and this happens. Like, for example, if you classically, you would say maybe in the 1960s and 70s, people were interested in, well, why can it happen so often that if you vary a parameter, you go from a steady state that's stationary to something that has small amplitude oscillations. Yeah? And well, you know, at some point people figured out, well, that's probably Hopf bifurcation. Yeah. And then people showed, okay, that's a generic type of thing that happens in nonlinear systems. And if you have one parameter, you can expect it, and so on and so forth. So how do these sort of explosive and non-explosive transitions with a trivial branch fit in here? So you can actually slightly extend or put a little bit of addition to bifurcation theory if you recognize that this can be sort of put into the standard bifurcation theoretic framework with a little bit of suitable sort of tweaking and tinkering. So first, some assumptions. I will not go through the mathematical assumptions in detail. So this was a talk sort of for a broad audience, including math, physics, biology, engineering, and so on. So the assumption is there exists this trivial branch for a main observable, like the infected density, for example. You assume that this main observable has a differential equation on iterated map that it's satisfying. Potentially, this X equation is coupled to a higher dimensional system. I will show you how to deal with higher dimensional systems like the 3-dimensional one, or even 5 or 10 or 100-dimensional one. Later on, there's a general strategy how you can do that. You assume that all the sort of dynamics for this low-dimensional observable is sufficiently regular and generic within a suitable space of smooth functions. Yeah, you will need a certain differentiability. For the mathematical experts, something like C3 should be sufficient in this case. So then the transition point you assume in the first parameter, meaning, for example, in the epidemic example, this beta parameter, we will call this parameter here P. In this first parameter, you indeed, along the trivial branch, you get a transcritical or a pitchfork bifurcation. And now the idea is, well, if you add a new effect, effectively always this new effect should have at least one additional control parameter. Makes sense, right? For this epidemic model, we had this W control parameter that was saying, well, if W is 0, there's no rewiring. And if you turn on the W, there's some rewiring. So at least we have one more parameter in the model. So by minimality, yeah, let us assume that there is at least one second parameter that influences the evolution of that observable. Yeah. If you do that, well, mathematically, what you do is near the bifurcation point, you Taylor expand. So first move the bifurcation point to the origin, you Taylor expand, and then you use symmetry of the, because you have made the assumption of the trivial branch, and then you use standard bifurcation conditions so that it's a transcritical or a pitchfork. And then after you did that, well, you truncate the Taylor expansion. You do a sort of rescaling transformation or blow-up transformation near the bifurcation point to sort of magnify the local dynamics near that point. If you do that and then you localize the whole dynamics near that point, then indeed you get as a sort of normal form for the transcritical and the pitchfork with the second parameter, the following sort of right-hand sides. And these C epsilon parameters with the superscript are actually small in epsilon, so you can make them as small as you like. And the 2, 0, 0, for example, this tells you, okay, it's for X has power 2, and then the P has power 0, Q has power 0, and so on. So that just give the indices of the Taylor coefficients. And you indeed see, if you do this normal form transformation, I hadn't seen this in any textbook, I have to admit. So that's why I did it myself. It's a relatively simple calculation on one page, just to make sure that I'm confident that this is correct, and didn't also find it in any paper. It's just a quite regular codimension 2 unfolding of a transcritical or pitchfork bifurcation, where indeed the codimension 2 parameter q appears in front of the nonlinear term. And clearly, if you vary the q, you can check that you can change the direction of the transcritical or the pitchfork from super to subcritical or vice versa, depending on what the value of q is. So generically, for a generic parameter q, if you have a second parameter in the model, and if you have a transcritical or pitchfork, this mathematical argument proves that indeed you can change the bifurcation direction. So what's the main picture? Well, the main picture is this. You have sort of not a one parameter, but a two parameter bifurcation diagram, where you have a codimension 2 bifurcation point. So you take the second parameter. If you vary it, then indeed you change the direction of that branch. So here at the back part, you still see it's supercritical or second order or soft. And then if you vary it forward and you vary the q, well, then it becomes first order or hard or subcritical. So an unstable branch bifurcates off backward effectively. And this is true for both the transcritical and the pitchfork. Well, so what are the steps now to apply this result? We should check whether such a mathematical result indeed applies in these high-dimensional network dynamics models. If we can apply it to all these models that can be found in the literature that have been developed with the sort of same story over the last 15 years. Well, first of all, you need to derive differential equations or iterated maps for the interesting observables from the network dynamics. That's often possible. Most often, these equations are quite big and coupled, but usually you can make them at least finite dimensional. And after you make them finite dimensional, you can sort of project them onto one dimension near the bifurcation point by center manifold reduction. And then you identify, after you center manifold reduce the whole problem onto this one-dimensional dynamics of this observable that you're interested in, you identify what is actually the effect on the adaptive or multi-layer or hypergraph structure on this parameter q. Yeah. Okay, let's try to apply this. Let's try to apply this to this adaptive SiS model. So here's again the three differential equations. So I will fix some parameters just to not gobble up the whole sort of picture. I will be concrete and try to fix all the other parameters that are not the parameters that are for the rewiring, just to sort of zoom your eye in to say, okay, only the W is left as a second parameter and the beta as a first parameter. If you do that and you do a center manifold reduction near the first transcritical bifurcation, it's about a 6-7 page calculation. Yeah, so you just sit down and you calculate the center manifold, you plug everything in, you get a one-dimensional reduced system in the center direction near the bifurcation point. You end up with this equation, and indeed this looks already like it should, namely, like we at least sort of conjectured from the abstract math that we derived, that there's a sort of main parameter that varies the linear part and that induces the transcritical bifurcation, which is this infectivity parameter beta, and that the sort of rewiring influences the normal form coefficient in the nonlinear part. So if you would relabel this a little bit and just set the W and interpret it like a Q, or formally a Q tilde if you're a mathematician, because it's of course not exactly the Q, but it's a sort of Q tilde that influences the Q, which is the entire second order coefficient. And then you set the first parameter to be beta. Then you indeed find that there's a transcritical bifurcation, and it goes from non-explosive to explosive at a calculable value precisely when this sort of part here, the term in front of the quadratic, that changes sign. And that's easy to calculate. You just check when this changes sign, and you get precisely that this sort of adaptive SiS model, when you add adaptivity and rewiring, so social distancing, there are parameter values where you can make this explosive. And if you can make that explosive, you can calculate, is that a special instance of this generic mechanism of a codimension 2 point of a transcritical or a pitchfork? Yes, this theory tells you it is. All right, well, let's do a second example that has been found in lots of the papers as well, has been discussed, a model that's very important for the sort of, also for the historical development of network dynamics. And that is the case when you are dealing with coupled phase oscillators. So here I don't take adaptive coupled phase oscillators or multi-layer coupled phase oscillators, where indeed you can again sort of change this, but I take higher order interactions or polyadic interactions. I've taken this model, or a reduced version of this model, from a paper of Skadal and Arenas that I mentioned before from 2019. So it's basically standard Kuramoto oscillators, which are individually just oscillating on a circle with a certain frequency omega k. They are coupled by a sine coupling to sort of first order. So two oscillators interact and adapt their phases by the sine. There's a coupling constant K2 that will be our first main bifurcation parameter. And then they also interact via triplets, via sort of higher order interactions, or, you could say they're interacting via hyperedge with three nodes, yeah. And then there's a second parameter that controls this triplet interaction, this K3. Yeah, you can derive these coupled phase oscillator models, for example, by a normal form near a Hopf bifurcation of general oscillators when there's coupled oscillators near supercritical Hopf, and they are generically coupled in a sufficiently suitable framework, which is laid out by Ashwin and Rodriguez in 2016. You get such types of models. So you get these additional terms. Yeah? And again, you can apply the steps. First, you sort of derive equations. You have them here. There are many. You need to reduce them to a low-dimensional model. So here we use the Odd-Anton's ansatz. If you don't know what that is, well, it's a special tailored ansatz that works very well for certain classes of Kuramoto models, meaning you can somehow reduce this Kuramoto model on an invariant manifold that is sort of low-dimensional. If you do that, you get an equation for the order parameter, which is effectively how synchronized the oscillators are. R is between 0 and 1. It tells you how in phase they are, or how out of phase they are. And you indeed find that there's a sort of phase transition or bifurcation from sort of complete disorder of the oscillators to partial order if you vary the K2, meaning there's a sort of stable steady state of oscillators being out of phase, and that stable steady state loses stability at the bifurcation point, which is actually a pitchfork bifurcation point at a certain value. Here in this case, it's K2 equal to 2. And then you see that, okay, this is a typical pitchfork, and indeed the K3, like we would expect and like it should in our theory, that enters is a new effect, which is the higher order interactions that come from these new higher order terms. It enters in the third order term. And indeed, if you, for these polyadic or higher order interactions, set x is equal to r, p is equal to k2 over 2 minus 1, and q is equal to k3 over 2, then indeed you see that you do get, well, again, it should be a q tilde mathematically, then you indeed get a pitchfork normal form, and you see that precisely the higher order interaction term, or the polyadic interaction term, changes the direction of the pitchfork from a sort of supercritical to a subcritical pitchfork. So it goes from non-explosive to explosive by adding these higher order interaction terms. And you can do this with all sorts of models. We did this with percolation. You can do this with multi-layer networks. You can do this with all sorts of other type of models. And you indeed see that in many, many, many cases, and mathematically, generically, you can prove that is the generic mechanism as long as you have a trivial branch, that this is precisely the mechanism that changes something that's non-explosive to explosive or vice versa if you add something to the model. All right, so here's a summary of my talk. So first of all, I told you how we identified by looking at the literature that there should be a universal mechanism. We found that mathematically, from the perspective of nonlinear dynamics, it's a relatively simple mechanism. Namely, it's a codimension 2 bifurcation in a symmetric system, where the symmetry comes from the existence of a trivial branch. And there are clear steps to apply this result in applications. So you take your system, you derive maps or flows, you reduce these maps or these ODEs or flows to a low-dimensional sort of problem on a center manifold. You calculate the normal form. You identify how the parameter that you added to your new model M star influences actually the second bifurcation parameter. And then you indeed can identify whether that's the mechanism. And as I say, mathematically, these will be satisfied by most models in a suitable precise mathematical sense. And we have checked this also in practice with several models like the SIS, Adaptive SiS, with variants of Kuramoto, and also with percolation type problems, which I haven't shown here, but you can look into the paper for that. Well, for more information and also for downloading links to the paper, please try to go to my website, which tries to be easy to remember by its name. And then I would like to thank you very much for your attention.